Okay, hey, welcome back. Today we're looking at 2.2 limits involving infinity. So we're just kind of building this idea of derivatives, right? So we're talking about limits, we're talking about the basics of limits. Last time when we talked about limits mostly as we approach particular numbers, like limit as x approaches 0, or limit as x approaches 2, and so forth. So today we're talking about limits involving infinity, and these are important because what they describe here are these two things. So these two things are something that you talked about in Algebra 2 and also in pre-calculus. So we're talking about end behavior and horizontal asymptotes. So if we can find what happens to our function as we approach infinity and negative infinity, it tells us exactly about our end behavior and our horizontal asymptotes. So yeah, so we can look at it in from a calculus perspective when we're talking about these things. So the first thing says use graphs and tables to find the limit as x approaches infinity of f of x and limit as x approaches negative infinity of f of x if our function is x over square root of x squared plus 1. So let's go ahead. I don't want to use this calculator again because it sucks, but we can show you how to do the calculator when you're in class. I can show you how to work them and do the graphing stuff because that's pretty easy to go over. But let's just do it in Desmos for now. So, sorry, x over square root of x squared plus 1. Okay, so we're going to do x divided by the square root of x squared plus 1. Okay, so that shows us our graph, and if we look at our graph, notice that this approaches, it looks like as we go further and further to the left, it approaches negative 2, and if we follow this graph further to the right, it approaches 2. What did I say? Negative 2 for the first. As it goes to the left, it approaches negative 2. As it goes to the right, it approaches positive 2. So the answer to this one, by using our graph, is very simple. So this is going to be equal to 2, right? As we go in the positive direction, as we head towards infinity, as we go to the right side, our graph looks like this. If we follow this, it looks like it approaches 2. If we follow this towards the negative side, that approaches negative 2. Okay, this time let's do the squeeze theorem. So you could graph this and try to check it out. In fact, we can do it now. Let's do sine x over x. Sine x divided by x. Now if we pull this all the way out, it looks like this is approaching 0 as we head to the left and right. So let's just use the squeeze theorem to verify, right? Because we're going to be working on squeeze theorem and getting better at it. So we're going to start off with this thing, sine x again, right? We know that the sine x, the values for sine x are always going to be between, they're going to be less than 1 and greater than negative 1. So they're between 1 and negative 1. Okay, so the problem is that this doesn't look like this just yet. But what we can do is we can divide each part by x. And then now it looks like something we can do. So limit as x approaches infinity. Now the cool thing about as x approaches infinity is that we're allowed to plug it in. However, it's not like 0, right? We can't divide by 0. We can divide by infinity. However, the thing is that we can only do it if there's a constant or if the x's cancel out. So let's talk about why that is real briefly. So let's say we have, let's look at this 1 over x, right? And we're trying to find the limit as x approaches infinity. So what's going to happen here is the x is going to get bigger and bigger. The top is going to stay the same. So let's say we did 1/10. Well, 1/10 is 0.1. Now let's make it a little bigger. Let's do 1/100th. 0.01. 1,000th. 0.001. So what's happening here is the bottom is getting ever and ever bigger, right? We're approaching infinity. So every time we increase the value on the bottom by a factor of 10, right, we move the decimal point. So what's going to happen here is if we get ever and ever closer to infinity, the bottom is growing infinitely large, the top is staying the same. What's going to happen anytime we do a constant divided by infinity, that's going to approach 0. Right, so this is going to be 0. The right side is going to be 0. And because the sine x over x is between 0 and 0, the limit as x goes to infinity of this whole thing, sine x over x, that's got to be 0. If the upper limit is 0, the bottom limit is 0, then it's got to be 0. Okay, so again, just some squeeze theorem. The more you practice it, the better, the easier it gets. That's all I can say. It's a little bit rough. It's one of the harder things to do, but they do ask it. So just know that when we're squeeze theoreming, we're putting an upper limit, we're putting a bottom limit, and we're trying to get it so that the upper and bottom limit are the same number, so that we can say that the function is equal to that one number. Okay. Oops. All right, so let's find the limit as x approaches infinity of 5x plus sine x over x. So the cool thing about this is we're just going to be applying algebra, and what we know from the last one that we did, the limit as x approaches infinity of sine x over x. And we're just going to, it's going to be nice and easy. So we're going to do algebra, and what algebra says is if we have a fraction like this, we can split it into two parts. So limit as x approaches infinity of 5x over x plus sine x over x, right? We're not substituting, we're splitting this fraction into two separate fractions because we have an addition or subtraction on top with just one term on the bottom. Okay? Now the cool thing here is 5x divided by x, well, those x's cancel out. And we know what the sine x over x is. Right, so the limit of this constant, there's nothing to plug that infinity into. That's just going to be 5. And then the limit as x approaches infinity of the second part, well, we just said the limit of as x approaches infinity of sine x over x is 0. So this whole thing is equal to 5. Okay, so the next part says the function g is a right/left end behavior model if the limit as x approaches infinity for the right side is f of x over g of x equals 1. And it's also the same thing, it's going to equal to 1 as well, but on the left side it's going to be from negative infinity. Limit as x approaches negative infinity. So let's look at this next example. We have f of x and we have g of x. So if we look at f of x, 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. If you graph that, that would be a curvy curvy polynomial function. In the middle part, it might look like, how much degrees is, okay, so something like this. Right, and then we have g of x, which is 3x to the fourth. It doesn't have these extras in here, so it's not going to be as wavy in the middle. But what it's saying is show that g of x models the end behavior of f of x. So let me write this down and we can graph it and just take a look at how cool this is. So 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. Okay, let's go to Desmos. So we're going to do 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. Okay, so this is like, well, it's pretty crappy, but it's hard to see, but it's very narrow. So what they're saying is that if we just do 3x plus 4, I mean, sorry, not 3x plus 4, 3x to the fourth, that even though the middle parts don't match up, the end behaviors are exactly the same. And it's kind of crappy to see this one, but if we pull this out all the way to the end, the end behaviors are pretty much the same. All right, so let's go back here and apply that thinking. So what this is saying is that even though the middles might be different, as we get ever and ever closer towards infinity, out towards the left and right, these are going to match up. So in order to show that, we just have to show that f of x divided by g of x is equal to 1. 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6 over 3x to the fourth. I should probably put that in the middle. We're doing the limit as x approaches infinity. And we could technically plug infinity here, but it's not going to help us. It's going to just make it worse. But if we separate this, so let's separate this into each part. So we're going to do 3x to the fourth divided by 3x to the fourth is 1. 2x cubed over x to the fourth, so that's going to be 2/3. And then there's 3 here, 4 here, so that's going to be just an x. Whoops. I want to cancel that. Let's change this a little bit. So we have the 2 in the numerator, the 3 in the denominator, and 1 of the x's left over. That makes it nicer. Okay, and then to the next term, the 3 and the 3 cancel out. That's nice. All of the x's in the top cancel out, but then we have x squared in the bottoms left over. And then for the next one, 5 over 3. One of the x's in the top cancels with one of the x's in the bottom, so there's still 3 x's in the bottom. And then actually 6 and 3 divide. It's going to be 2 over x to the fourth. Now, the cool thing about it when we separate this up into little fractions is that now we can do the limit with infinity, because each of these things, when I plug infinity in here, 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 and here, because the tops are all constants, the limit is going to be 0, limit is going to be 0, limit is going to be 0, limit is going to be 0. So 1 minus 0 plus 0 minus 0 plus 0 is all going to be 1. So the limit as this thing approaches infinity is 1. So we just showed, right, because we said that if we divide the top and bottom and it's equal to 1, then the g of x is a model of f of x. All right. That might be a lot, but it's not too bad. Like, the math on it and the concept behind it is not too bad. It's just the process of doing it. It takes a little while. Okay, find end behavior model. So the easiest way to do this, right, when we're asked to find them, is we're gonna knock off all the parts that are not leading terms, right? So on the top and bottom. So we get rid of all the lesser degree terms. So we're left with 2x to the fifth over 3x squared. So we have 2/3, x squared, and x to the fifth. We cancel 2 in the bottom with 2 in the top. So we're left with 3. So this would be our end behavior model for this function. Okay, likewise here, we're going to knock off all the lesser degree terms. Oh, x cubed and x cubed also cancel out, right? So this is going to be 2/5. So if you think back to the rules of end behavior, the rules of horizontal asymptotes, one of the rules was that if the top and bottom are the same, right, we get the fraction of the coefficients, which is what we just showed using calculus. And then here, if the top is bigger than the bottom, then we get an oblique asymptote. Right, meaning that it's not just going to be a horizontal line. It's going to model x cubed, 2/3 x cubed. That's going to tell us what our end behavior looks like. Okay, and then again, if we have like 2 over x minus 1, when the degree on the top is less than the degree on the bottom, this is going to be 0, right? Because when we plug in infinity to the bottom, or as we're approaching infinity on the bottom, we know that this always goes to 0. So just the connection between Algebra 2 type stuff and the higher level of calculus. Now that we can talk about limits and limits as we approach infinity and negative infinity. Oh, that's it for today. All right, good job today, guys. Hopefully it wasn't too much, but small recap. Okay, so we're saying that we're looking at limits involving infinity. So we're talking about end behavior and end behavior models / horizontal asymptotes. So we use the graph first, right? We use our graphing technology. We said that as this approached infinity, the graph looks like it was approaching 2. As we approach negative infinity, it looked like we are approaching negative 2. On the next page, we determined using the squeeze theorem the limit as x approaches infinity of sine x over x. So just some more squeeze theorem practice. Next, we did it algebraically, right? We split this fraction into 2 fractions and found the limits of each part. We knew the limit as x approaches infinity of sine x over x was going to be equal to 0. And then algebraically, the 5x over x canceled out nicely. We were able to find our limit pretty easily for that one. Then we talked about end behavior models, right? So we said that if we're given an f and a g of x, if we divide them and it's equal to 1, then we know that the g of x is an end behavior model of the f of x. And then we ended up just finding the end behavior models, connecting the idea back to horizontal asymptotes and our ideas of horizontal asymptotes from Algebra 2 and pre-calculus. All right, so if you have any questions, please bring them next class. Good luck. Good job today.